I'm going to talk about AI, biology, and technology. The last 10 years of computing has been very exciting. We're seeing neural networks achieve state-of-the-art results across an enormous range of applications. So amongst all of this success, it's worth taking a step back to think about why we're seeing artificial neural networks achieve such success. So if you go back to 2012, that was when we saw the first neural networks applied to the ImageNet competition, and they outperformed classic techniques. We then saw subsequent versions outperform humans, and this was a big deal because this was one of those classic problems that's so easy for humans, yet had thwarted computers for decades. We then saw new neural networks applied to more and more vision tasks, then onto speech and language tasks. And now we're actually at the point where we're seeing neural networks applied to most difficult problems, even EDA. So why do neural networks have this universal applicability? Why can the same tool be applied to so many different problems? Well, there are two key points I like to make when reasoning about the success of neural networks. First, if you look at neural networks from a mathematical perspective, they're actually universal function approximators. So they can approximate any arbitrary function in any arbitrary space. And in many of these difficult classical computing problems, we're using heuristics to approximate some unknown underlying function. And when given enough data, neural networks can actually do a better job at approximating these unknown functions than classic techniques. So if you think about neural networks that way, we should not really be surprised when we continue to see neural networks achieve state-of-the-art results in new fields. Second, while neural networks were originally inspired by biological neural networks, there actually was very little evidence linking the two. But over the last few years, that's actually changed. So with the advent of new technologies in neuroscience, neuroscientists have actually been able to record from clusters of neurons in a controlled environment. And we're actually starting to see evidence that the abstract computations performed by neural networks are similar to those performed by the brain. We've seen this in visual cortex and medial entorhinal cortex. So with neural networks, we've got this tool with this universal applicability, and there's now evidence that it performs the same type of computation as the most successful universal tool ever created, which is the human brain. So my job at ARM is to help create the technologies which will enable the ARM ecosystem to develop and grow in machine learning. And when reasoning about how the digital ecosystem will develop, we can actually gain inspiration from looking at how the human brain develops. So what I'm showing here is something called the human plasticity curve. This is a well-known curve in the field of neuroscience, and it captures how different functionality in the brain develops. And in this case, we're actually zoomed in on the first year of human life. So with the first curve, the orange curve, this actually captures the development of the sensor systems like vision and sound. And the second curve, the yellow curve, actually captures language and language abilities. And this shouldn't be a surprise to anyone with kids or nieces and nephews, because these development phases are actually really apparent as toddlers develop. So interestingly, actually, the developments in the digital ecosystem have followed the same phase. So the first artificial neural networks were around vision and sensor systems like voice. And today we're actually seeing countless vision systems using neural networks deployed on ARM platforms, from surveillance cameras to autonomous vehicles. And then we actually saw user interfaces pervasive and found in many homes. And we've seen a huge advancement in natural language processing, and we can now actually deploy NLP models like MobileBERT on resource-constrained devices like ARM phones, where they assist in actually many different NLP tasks. So in the digital ecosystem, we've done all these great things, and we've solved these really challenging problems. But from a brain perspective, we're actually still in year one. We're still in that toddler phase. So what comes next? So if you zoom out, actually the next plasticity curve is human cognition. And there are a couple of things I like to point out when talking about this. So first, the timescales of this curve are significantly longer than the others, so they don't stabilize until the late teenage years. And second, actually, neuroscientists don't have a deep understanding of how the different components of the brain give rise to cognition. So not neuroscientists, not philosophers. I'm not going to stand up here and tell you that I know. But actually, there are some things that we actually know about the brain, and it's safe to assume that those things are necessary ingredients for that cognition, even if we actually don't understand the underlying recipe. So what are these ingredients? Well, I think first it's worth noting that the brain is actually not just a gigantic neural network, but it's actually a collection of specialized processors. And these different specific neural networks are optimized for given tasks. So there are regions of the brain developed for vision, for auditory motor movements, balance, memory, and working together, these components can achieve all the amazing things that humans are capable of. And so if we really want to enable that blue curve, we're going to need to add more compute. And this is eloquently captured by Huang's law. So we need a relentless focus on increasing the amount of compute in a given area and power budget. Second, we need to focus on the right type of compute. So while different regions of the brain may be optimized for different tasks, they're actually still built from the same underlying building blocks. So the connectivity may be different. For example, the visual cortex is very feed forward, while the hippocampus has significant recurrence, but actually the underlying building blocks are the same. There's actually evidence for this in that if a ferret is born blind, part of the visual system will actually be repurposed for the auditory system. And so by focusing on the right building blocks, we can optimize and continue to push the envelope of compute in ARM ML platforms. And third, each region of the brain is actually the result of millions of years of evolution, successive kind of fine-tuning to optimally solve a task within a given budget. And when we want to create new artificial neural networks to solve problems, we actually don't have the luxury of millions of years of evolution. So we need to develop tools to kind of short-circuit that evolution and enable quick exploration of neural network architecture. So we need to increase the amount of compute. We need to focus on the right type of compute. And we need to create tools to explore new neural network architectures. So I've just described some of these ingredients, which I think are required for the next phase of artificial neural networks. And now let's talk actually about some of the specific concrete things that ARM is doing based upon these principles to drive our technology. ARM has and will continue to have a roadmap of features and improvements to the architecture, which greatly improve machine learning performance. We started with version 8.4 of the architecture, where we introduced the dot product instruction. In version 8.6, we added matrix multiply instructions, which further improved performance. We've added new floating point formats specifically designed for machine learning, like bfloat 16. And of course, the architecture supports wider vector widths, which will be important for ML performance as well. Many of these features will be present in the Neoverse V1 coming soon. We've also worked to create optimized library routines for V1 utilizing these new features. And these will be released via our optimized ARM compute library. The rightmost bar on this graph shows SME, which is the scalable matrix extension to the architecture. So what we've done here is we've actually added the ability to perform an outer product operation into a 2D destination operand. And by doing this, you can get great reuse of your operands and really increase the amount of ML throughput in your system. And adding all of this up to SME, we're looking at a nearly 100x architectural improvement in ML throughput. And this is just architectural, so it doesn't account for process node, it doesn't account for frequency. Of course, it's more than just adding instructions. You actually need to be able to achieve that performance and unlock that performance with real-world software. So what I've shown here actually is a curve of the results from an internal benchmark, which show we're able to achieve close to the speed of light on those benchmarks. Similarly, in our GPUs, we've been pushing the envelope of our GPU performance. So going from G76 to future GPUs, we're looking at a nearly 5x speed up in ML capabilities. And this is starting from G76, which was already a very heavily optimized piece of IP. And of course, again, it's more than just adding instructions and improving hardware IP. We also have to provide the software, the tools, the libraries to enable that ML performance. We've released our ARM open source compute library, which is a source of optimized kernel implementations for CPUs, GPUs. We also have released the optimized ARM-NN inference engine, which is open source as well. These curves here actually show that we're seeing a 2x speed up just from software improvements alone. So same IP, same neural network, just from continuous software improvements, you can get a nice performance boost. And we've been working really closely with the Android team to ensure that these new ML-related features in the latest IP can be immediately used via standard Google APIs like NNAPI and TF Lite. So when silicon with these new features is actually available, the performance will be immediately unlocked underneath those APIs. So by continuing to improve the IP and releasing our open source software, which we also continue to improve, you can see tremendous gains in the actual amount of ML compute possible in ARM platforms. All of this increase in ML performance is certainly noticeable in the world around us. ML, it's more than just exciting new technology like robots and self-driving cars. It's a lot about just making existing things better. I've seen quite a few interesting examples and products lately that demonstrate this, and I'd like to share a couple of these with you. Relijet's AI-powered hearing aid, the AutoAD, intelligently separates different sounds through microphone-enabled processors. So actually using a neural network running on a Cortex-M processor, the AutoAD more accurately mimics how your brain would hear sound if your hearing wasn't impaired. It also has the power to separate and enhance incoming voices from two different speakers and actually provide noise cancellation in loud environments. And it does this all very efficiently using a rechargeable battery that can last all day. The second example is we've been working with Archlick to develop an ML-based refrigerator control system. So the small but mighty Cortex-M is actually a good fit for the processing requirements of the ML compute in this system, and they've used Cortex-M software libraries, tools, and optimization flows. And we're actually seeing energy savings of upwards of 10% in our AI-enabled fridge. And I think this is just the beginning. So, today we talk about a more efficient refrigerator. Next, it will be microwaves, dryers, every appliance, power plants. Everything will be made more efficient by ML. Now, if you really want the best possible machine learning performance, you need a piece of IP that was designed from the ground up for machine learning. So I'd like to talk a little bit about our micro NPUs, the Ethos U55 and Ethos U65. These designs were created for best-in-class ML performance by utilizing some key technologies we developed internally, like weight compression, where we have a custom codec which can compress models all the way down to 2 bits per weight. We focused on fixed function hardware for common operations, resulting in best-in-class perf per square millimeter and perf per watt. These designs were designed from the ground up to be integrated into embedded systems, so they work very well with systems with shared SRAMs. Integrated into embedded systems, so they work very well with systems with shared SRAMs. And our compiler stack, which we co-developed, will take into account the specifics of your memory system and use advanced technologies like cascading across layers in order to schedule your neural network down to the underlying system. And this is all enabled via an open source software stack integrated under the TF Lite micro inference flow developed closely with Google. And on that note, I'm very excited to share that our partner Aleph recently launched a series of AI-enabled and power-efficient microcontrollers and fusion processors, the Ensemble and Crescendo product families. And these actually feature the first in-silicon instance of the Ethos U55. These are some amazing power-efficient devices from the team at Aleph that integrate AI, ML acceleration, multi-layered security, LTE, NB IoT connectivity, and other tech. It's very impressive. So we actually have Aleph silicon in our lab, and we've been measuring the performance on an object detection neural network, and we've seen a 75x performance improvement running on the Ethos U versus the M55. Now that's compared to the M55, which is already 10x better than previous microcontrollers like the M4. Now, this is a great example of specialized processing and really what's required if we want to enable the next level of machine learning performance on the edge. Aleph Silicon and the TF Lite Micro software stack are available now for developers. And actually, there are more partner announcements coming up, so continue to watch this space. Now, there's more announcements coming up, so continue to watch this space. Now, there's more to neural networks than just max. Neural networks are actually sophisticated graphs of tensor operations. The number of different types of tensor operations is actually continually increasing, and researchers are inventing new types of operations every day. So the task actually for us as system designers is how do we create an optimized platform that can achieve great performance on existing neural networks while still leaving room for new types of graphs and new operations in the future. So I'd like to talk a little bit today about a project that we've been doing in the open source called TOSA, which stands for the Tensor Operator Set Architecture. When we started on TOSA, we had a hypothesis that most tensor operand source called TOSA, which stands for the Tensor Operator Set Architecture. When we started on TOSA, we had a hypothesis that most tensor operations in common frameworks could actually be reduced to a sequence of simple tensor operations. And the inspiration for this was really from the early days of CPUs, where early CPUs had complicated CISC instructions, and eventually the industry realized that with a finite set of simple RISC instructions, you could compose any of those complicated instructions. It's then a much easier problem to create an optimized system for that finite set of simple instructions, and the result is something that's more efficient because you're focusing on these simple primitives. So we surveyed the TensorFlow inference operators, and we created a spec of 67 tensor level primitives, which can be composed to support most of the TF operations. We've open sourced this dialect into the MLIR mainline. It's actually the first tensor dialect in MLIR mainline. And we've also open sourced lowerings from TF and TF Lite. We've published the spec, and it's open for contributions. We've actually designed the spec and the architecture, more like an architecture than an API. So the precision around things like quantization are very rigorously specified. We're also in the process of releasing a conformance suite for TOSA, so platforms supporting TOSA can provide a consistent experience. So here's an example actually showing a lowering of a common activation function being lowered down to that sequence of simpler TOSA primitives. As I mentioned before, the neural networks in the brain have been highly optimized via evolution over time. And we don't have that much time, but actually we do have lots of compute. And we can use that compute to enable quick exploration of new neural network models. And within ARM, we actually believe that neural architecture search, NAS, is actually a very promising technology with the potential to automate neural network exploration and design. So we've been working on this internal tool called Bumblebee, where we're actually exploring NAS technologies. The Bumblebee system is designed to create optimized neural networks for a given platform under a certain set of constraints. So at a high level, you can give the tool a search space. You can tell it which platform you'd like to target, Ethos A or Ethos U or Cortex A, and you can give it a latency target. And then the tool will search and attempt to find the best model achieving those targets for that given platform. So here's actually an example of two different super resolution networks generated by the tool. One is for Cortex A Graviton and the other for Ethos U. And they look different because actually the best network for one platform may not be the best for another. So we think that these types of tools are inevitable. We're going to continue exploring these technologies, and we'll be looking for ways to enable this type of tech in the ecosystem. At the very beginning of the talk, I mentioned that we've been seeing evidence that artificial neural networks perform the same type of compute as biological neural networks. I also talked about how the third phase of brain development is based upon cognition, and that neuroscientists really don't deeply understand what gives rise to cognition. So here's a little more neuroscience. Several decades ago, it was hypothesized that there were neurons or regions in the brain that could represent a concept or an abstraction. So, for example, you could have a collection of neurons that responded to the concept of a president. And so these neurons would fire not just when shown pictures of the president, but when shown pictures of many presidents or pictures of president-related items like the White House or political parties. And the idea was these cells are representing this abstract idea of a president. And I think you could argue that this higher level representation of an idea or a concept may be a tiny step up the way that blue cognition curve. So a few years ago, neuroscientists actually discovered in the human brain in living patients. Neurons which exhibited the same type of behavior. Now, it had only been hypothesized before. But in this case, it was actually for a particular famous person. So the neurons would respond to pictures of the person, drawings of the person's name, decades earlier. So that was a very exciting discovery in neuroscience, but actually what was doubly exciting is that recently, OpenAI noticed that neurons in the hidden layers of their CLIP artificial neural networks exhibited these same properties. So these neurons in the CLIP network fired in response to the concept of Spider-Man. They would fire with pictures of Spider-Man, drawings of Spider-Man, and actually the word Spider-Man. And so this is another example, actually, of neural network behavior matching that of biology. Now, while this idea of neurons which can represent concepts is still far, far off from cognition, perhaps it's a small step towards the higher level abstractions that we'd actually need to eventually enable that blue curve. And we're already seeing this in artificial neural networks today. So, where do we go next? What's next for the digital ecosystem? Well, like I said at the beginning, we don't have a deep understanding of what gives rise to cognition, and we definitely won't anytime soon. But I actually believe that if we continue on our current path, if we continue to enable more compute, if we focus on the right computational primitives, the right type of compute, and we create an ecosystem around those primitives, and if we actually continue to develop tech for the rapid neural network exploration, I think if we do all of these things, we may perhaps get out of that toddler phase and grow up a little bit. Thank you.